Alrighty, so now we've added the m over ei values to our diagram down here, and we've drawn our elastic curve based on the loading and the support configuration. My logic for this is that we had a 400 kilonewton load here and a 200 kilonewton load here, and this length is cantilevered, meaning that there's going to be a deflection here no matter what, and it's going to govern the deflected shape because this length is also cantilevered with that max load. So we have the most severe deflection at point C, and the rest of this elastic curve is going to follow uh, the curve based on this assumption, right? So we have the deflection down here, coming back up and bowing between A and B, and that's our deflected shape. Now, the important thing to begin to visualize in this problem is where our tangents are going to lie. And a general rule of thumb is to always apply them at the supports and to apply them at points of interest. So we have two supports here at A and B, and we also have point C, which is our point of interest since we need the deflection there. Let's go ahead and add our tangent lines. Now our tangent lines have been added, and let's just go through what's going on here. We have a tangent at B, which is following that elastic curve, obviously. So we see it extending all the way from point C all the way to point A, and we're going to be using all of these tangents as references to solve our problems here. So we have the tangent at B, we have the tangent at C as well, based on that curve we've estimated, and we have the tangent at A. Now, what's next? We have to also consider the tangent deviations for these important points as well. So you have point A, point B, and point C, which we all need to consider. So let's add those as well and talk about what those mean. Alrighty, so now we have all of our tangent deviations plugged in that are going to be important for this problem. And we'll notice that the format for naming these is going to be A, B in this case, meaning that we're going from point A to the point of intersection with respect to tangent B. And that's similar for all of these other tangent deviations, going from point B on the elastic curve to tangent A, and we're going from point C to tangent A. And these points are all with respect to the elastic curve, not to be confused with the member, all right? So what is our problem asking for? It wants deflection and slope at point C. So let's try and solve for some unknowns at point C. So one that jumps out right away is this TCA. So what does that mean for us? It means that we're going to be solving for the tangent deviation from point C to point A, meaning that we need to find this x value with respect to each different moment segment we're passing through on this m over ei diagram from point C to point A. So I went ahead and added a visual down here just so we can see what's happening with this x value as we're using this formula for TC to A. And we are taking the x values between C to A, and we're taking the m over ei area segments, or the resultants that we solved for each of these different segments that we pass through. So we're going from C to A, meaning that we're actually going to go through each different segment. So that means there's a different x value for each one. So for this first segment, since we're starting from point C, we are first passing through segment 4. So what is this going to look like in our formula? The first thing we have is this value of 2 over 3 times 10. What is this? This is the length. So we have 10 meters between C to B, and we have the location of that resultant, which is 2 over 3 from that point C, since it's a triangular shape. And we're simply going to multiply that by the resultant of that m over ei diagram, which is negative 5,000 over ei. We do the same thing for segment 2, except now we are including this length that we are passing from C to B, which is 10, and then we are taking, once again, the centroid for this triangular shape, and since the larger end is closest to us, we are now taking 1 over 3 in this case, times the length of the segment, which is 5 meters right here. So we have 5 there, and we are once again plugging in the resultant value for the segment we're referencing, which is this triangular shape number 3. So we have negative 1458.3 over EI. We do the same thing for segment 2. This is a rectangular shape, so that means it's going to be half of this 5 meters. So we are once again taking that 10, which we have already passed, and we're adding that half of 5 meters, which is going to be 1 half 5. Once again, we are multiplying it by that resultant for the m over EI segment we're referencing. So we have negative 3,750 over EI. And lastly, we are taking this segment 1 here, going from point D to point A to finish off. And that resultant is located at 10 plus 5 plus 1 over 3 of 15. So 10 plus 5 plus 1 over 3, 15. And that is times the resultant value, which is negative 16,875 over EI. Solving for that, we are left with TCA, which is equal to negative 4,000 or 43,400. Oh, Jesus, this number's a lot bigger than I thought. 434,721.8 over EI. Now, this value is negative. We're going to talk about what this negative means right here. So we have tangent deviation from point C on the elastic curve to the tangent intersection on tangent A. So since point C is below point A, this should be a negative value. And since the first reference point in this formula is below the tangent line, that value is negative, meaning that our representation of the elastic curve is currently correct and our sign is adequate because this point C on the elastic curve is below. So we're thinking positive above, negative below. That is why this value is negative. Okay. Now, the next thing we need to do is start to solve for this delta C, or the deflection value that we're looking for. But how can we solve it? We have this TCA here, and we have this delta prime that I've drawn for some reason, and delta C. So the reason I've drawn this is because we can create a relationship to solve for the deflection at C. And that is simply by taking this absolute value of this tangent deviation, TCA, which we have just solved for, and we are taking away this delta prime that is still unknown. Now, why am I taking an absolute value here? I'm taking an absolute value because we can see visually, just from this diagram, that we need to be taking away from this value. So we can't mix the signs in this case because it will just simply create confusion. And we also understand that this value is being subtracted from based on this delta prime, right? So we are taking the absolute value of TCA in this case. Now we still don't know what delta prime is, but we do know that we can solve for TBA because we have this M over EI diagram. And if later on we can relate these two triangular shapes by similar triangles, then we can get that delta prime and solve for delta C. So let's start by solving for TBA, and then we'll get into the similar triangle part. So we're doing a very similar thing. Let's draw the x values that we need to reference in order to solve for TB over A. Alrighty, so here they are drawn on the diagram. We have 3 separate segments that we are passing for when we go from point B to point A. And we are going to use that similar formula that we have already previously used. And we can start plugging in. We know that this length is going to be 1/3 of this triangular segment's length, which is going to be 1/3 of 5 meters. So we have 1/3 of 5 meters here. Taking that value once again. This is simple stuff now for you guys, no problem. This is easy peasy. We move on to the second segment. We are taking 1/2 of the rectangular segment number 2 here. So we have 1/2 of 5, taking that value once again, which is negative 3,750 over EI. And lastly, we are taking that positive value, and we're going to add the 5 meters and then take 1/3 of this 15 meters here to get to that resultant centroid, okay? So we have 5 plus 1 over 3 of 15, and we are taking that resultant once again, which is negative 16,875 over EI. Solving for TBA, we are left with negative 180,555.5 over EI.
Got
Okay,
it.
so now we've updated our drawing. We've added the values for the tangent deviations of AB and CA over here. And I've also added some angles of interest that are going to be super important for the slope later on. But we're going to explain that in a bit, so don't worry about it for now. Let's look at the similar triangle that we were talking about. We have the relationship between delta prime, which is what we're interested in order to get to that final delta C. And we could relate that to the tangent deviation BA over 20. And that'll look something like this. We have delta prime over 30 is equivalent to the relationship of TBA. We're going to take that absolute value as we explained earlier. And that value was solved for. That's absolute. And then we have it over the 20-meter distance. So this relationship will allow us to solve for this delta prime, which will be equal to 270,833.3 over EI. And who remembers the formula that we were solving for previously? We have the absolute value TCA subtracting this delta prime will give us the deflection at C. So solving for this finally, we can plug into our formula. Let's bring 1 over EI outside of it and plug in for the values that we have. So we have TCA, which is this value right here. We have 434,721.8, and we are subtracting this value that we just solved for. So plugging that all in, we're left with a deflection at C equal to 163,888.5 over EI. And we can see from this diagram right here that this value is going to be downwards with respect to our original member. So now let's look at the slope that we need to solve for at C. Okay, so now that we have delta C, let's go ahead and figure out what theta C is. I just want to preface this by saying I had tan B written here earlier. I actually erased it because it was obviously in the wrong spot. And TBA was equal to TAB, so I erased that as well. So I apologize if that was confusing a bit earlier, but now everything should be okay. And we can proceed with the problem. I've drawn angles or relationships all over this drawing just so that we can relate different ways of solving for these angles that are comprising theta C. Now, what angles are actually equivalent or sum to make up theta C? Because we can't solve for theta C right away. Well, we have theta B, which is the angle created between the original neutral axis of our member to the tangent B. We also have theta BC, which is between tangent B to tangent C. And these will add together to make up theta C. So that's the first big relationship that I would have written down for this problem. So theta C is going to be equal to the absolute value of theta B plus the absolute value of theta BC. Now the second part of this problem is how can we solve for these two? Theta BC will be super easy, and we can get to that using this formula here. The trickier part of this formula is figuring out what theta B is, which is why I've drawn all these relationships in order to figure out a way to solve for that. So we can solve it by figuring out that, okay, theta B is the angle created between tangent B and the neutral axis. So we have a theta B here, but we also have a theta B on this side as well. So if we solved for the tangent deviation AB, we can create a relationship between that theta B and TAB since we have the known length between the two. So that will be a simple relationship that we can solve for, and I'll show you what that looks like when we get to it, okay? So the first thing we need to do is solve for TAB. Now, what is that going to look like? We've done this 2 times before, so I don't want to go into too much detail, but we're going from point A to point B, and we're taking all of the x values that we're crossing between each of these resultants in the M over EI diagram. So you have 1, 2, and 3 being passed through, and this length will be 2/3 of 15. This length will be 15 plus 1/2 of 5. Then this length will be 15 plus 2/3 of 5. So let's start plugging in and see what that looks like. Now that we have TAB solved for, we can finally solve for theta B, and that's simply going to look like this. We have an opposite over adjacent relationship, so we have theta B will equal to the absolute value of the tangent deviation TA over B, and that is over the length of 20, and we're neglecting that tan inverse value just since these values are super small, and we are just plugging these values right into the formula and solving for that theta B. And theta B will equal to 13055.5 over EI. And we can see based on this diagram that this theta B is going to be a clockwise rotation, right? So we'll just draw an indication right here that it's going to be clockwise. Now let's go ahead and solve for the second part of the formula that we're trying to get, which is this BC value. So theta BC is going to be simply equal to the resultant between B and C. And we only pass between these 2 points, therefore we can simply get this value of 5,000 over EI. And we just go ahead and finally plug into our theta C formula, which will be equal to 1 over EI pulled out, 13055.5, and that's for the theta B that we just solved for, and we are adding that 5,000. Once again, taking the absolute values, right? Leaving us with a final value for theta C of 18055.5 over EI. And once again, let's take a look at this diagram here. We are going to have a clockwise rotation.